At the end of this chapter, you'll be able to identify and locate the components of the pneumatic, air conditioning, and pressurization systems. Describe the layout of the pneumatic, air conditioning, and pressurization systems. Identify their subsystems and interfaces. Explain the operation of the pneumatic, air conditioning, and pressurization systems' main components. Identify and explain the controls associated with the pneumatic, air conditioning, and pressurization systems. Identify and explain the indications and enunciators associated with the pneumatic, air conditioning, and pressurization systems. The air system of the ATR 72-500 has three primary systems: pneumatic, air conditioning, and pressurization. The engine's compressors through the engine bleed valves supply pressurized air to the air conditioning and pressurization systems. Its temperature is controlled by the packs, and then it's distributed to the pressurized zones. Finally, it's discharged outboard through two outflow valves and partly recirculated. The MFC monitors the system and alerts the crew in case of a system malfunction. The pneumatic system is composed of all systems designed to supply air to the aircraft consumers, including the associated controls, monitoring, and indicating components. The consumers of bleed air are the air conditioning system, the pressurization system, and the ice protection system. A leakage detection system provides protection against an overheat around the hot air ducts. You'll hear more about the pneumatic system in upcoming lessons. In this lesson, the air bleed system will be explained in detail. The needed air is bled from the engine compressors at the low pressure or high pressure stages. The system automatically selects the compressor stage from which air is bled depending on the pressure and/or temperatures existing at these stages. It also regulates the air pressure in order to avoid excessive pressures. In general, the low pressure stage provides air, but if the pressure from the low pressure stage is insufficient, the air source is automatically switched to the high pressure stage. This may occur during ground operations and during descent with flight idle power set on the engines. The high pressure valve achieves the transfer of air. This valve is a pneumatically operated and electrically controlled butterfly valve that remains closed in the absence of electrical power. When the high pressure valve is closed, air is directly bled from the low pressure stage. If the high pressure valve is opened, air is bled from the high pressure stage and admitted into the low pressure ducting. There is no recirculation of high pressure air into the low pressure stage because the high pressure air closes the check valve. For the engine and wing de-icing systems, high pressure air is always bled from the high pressure stage through an electrically controlled pressure regulating valve. Now let's take a look at the bleed valve. Downstream of the junction of the low pressure and high pressure ducting, a pneumatically operated, electrically controlled butterfly bleed valve admits air into the duct. This valve acts as a shutoff valve. It has a single solenoid that closes the valve when de-energized. The bleed valve automatically closes when a bleed duct overheat is detected, a bleed duct leak is detected, the associated engine fire handle is actuated, an engine failure occurs during takeoff, and the propeller brake is selected on for left bleed valve only. If there is no air pressure, the valve will be closed by a mechanical spring regardless of electrical power supply. Note that the opening of the bleed valve is inhibited during the engine starting sequence. Another important valve in the pneumatic system is the ground crossfeed valve. It connects the left and right air bleed systems and is a spring-loaded, closed, solenoid-controlled pneumatic shutoff valve. The two states of the ground crossfeed valve are opened and closed. On the ground, it is always open, except when both engines are running and the propeller brake is disengaged. In flight, the ground crossfeed valve is always closed in normal operation. For safety reasons, the ATR 72 has a continuous monitoring system to detect overheating due to duct leakage that protects the structure and components in the vicinity of hot air ducts. This protection is available in the wing leading edge and wing to fuselage fairing, in the upper and lower fuselage floor, and in the air conditioning pack area. In order to ensure rapid leak detection, a Kevlar envelope is installed around the major parts of the high-temperature ducts in order to collect and direct leaking air to the sensing system. The sensing system has two single-loop detection assemblies for the left and for the right air duct systems. The sensing element consists of an energized nickel wire embedded in an insulating material. The insulating material is connected to the aircraft ground. When it is being heated, the insulating material loses resistance and the nickel wire is connected to the aircraft ground. This occurrence is processed in a control unit that will generate an alert signal and illuminate the respective leak light. After a 1-second time delay, the associated pack valve, the high-pressure valve, and the bleed valve, including the ground crossfeed valve, if the left loop is affected, will close automatically. An overheat control system is installed on the aircraft. It's composed of thermal-resistant switches installed on the engines near the high-pressure compressor exit. These switches are duplicated for safety reasons and controlled by the MFC system. They ensure that the bleed valve and the bleed air shutoff valve are closed whenever an abnormal over-temperature occurs. Note: leak and overheat are always associated with a high temperature. In case of overheat, the associated bleed system may be recovered after a cooling period, but in case of leakage, the crew must consider the associated bleed system as inoperative for the rest of the flight. When the bleed valve position disagrees with the selected position, the associated bleed and pack fault lights illuminate amber. The CCAS is activated and generates a master caution flashing light. The amber air light on the CAP illuminates and a single chime sounds. In case of bleed duct overheat, the associated overheat, bleed, and pack fault lights illuminate amber, and the CCAS is activated, which generates a master caution flashing light, illuminates the amber air light on the CAP, and sounds a single chime. In case of a detected leak, the associated leak, bleed, and pack fault lights illuminate amber, and the CCAS is activated and generates a master caution flashing light, illuminates the amber air light on the CAP, and sounds a single chime. When the ground crossfeed valve is open during its normal operation, the crossfeed valve open light illuminates amber. When the ground crossfeed valve is open, when it should be closed, the crossfeed valve open light illuminates amber, and the CCAS is activated, generating the master caution flashing light, the amber air light on the CAP, and a single chime. The air bleed panel is located on the right side of the overhead panel. This panel comprises the engine bleed push buttons, the overheat lights, the leak lights, and the ground crossfeed open light. The engine bleed push button can be selected to on when the push button is depressed, off when the push button is released. It is also fitted with an integrated amber fault light. Now let's see what happens when you use the different modes. When selected on, the associated high pressure and bleed valves solenoids are energized, thus allowing them to open if pneumatic pressure is available. When selected off, the associated high pressure and bleed valves are closed. The off light is illuminated white. There is a magnetic indicator and a leak test push button available for the air bleed system on the right maintenance panel. They're used for maintenance purposes only. The bite-loaded magnetic indicator indicates that the left or the right high-pressure valve actual position disagrees with the closed selected position. A push-to-test push button allows checking the functioning of both overheat detection circuits along the bleed air ducts. When depressing the push button, both leak amber lights illuminate on the overhead panel. The ATR 72 is equipped with 3 air sources, 2 packs, and an interconnection for a low-pressure ground unit. The ground unit, through an external connector, may be used for air conditioning. The air conditioning system takes air from 2 packs. These 2 packs regulate airflow and the temperature as required. The packs are located in the main landing gear fairing. They work automatically and independently. The left pack supplies conditioned air to the cabin and to the cockpit, while the right pack supplies conditioned air only to the cabin. If one pack is not working properly, the other pack supplies both compartments through the mixing chamber. The air is cooled, compressed, and dried, and prepared for delivery to the cabin. A pack has 2 flow levels available, the normal and the high flow. When operating in high flow, the pack entrance pressure increases. This helps the pack to perform better in outside high temperature conditions. Air cooling in the heat exchangers is always performed on ground by 2 ground turbofans, 1 for each pack, via a turbofan shutoff valve. In flight, it's performed by the respective ground turbofan if the airspeed is below 150 knots and the landing gear is extended or retracted for less than 10 minutes, or by ram air when the airspeed is above 150 knots. Note that in case of engine oil low pressure, the turbofan automatically starts on the opposite side and runs as long as the indicated airspeed is below 150 knots, regardless of the landing gear position. Also note that an incorrect position of a turbofan shutoff valve leads to the closure of the associated pack valve. Let's take a deeper look inside a pack. Hot air from the respective engine is admitted through a pack valve, which is pneumatically operated and electrically controlled. Due to its spring load, the pack valve closes without air pressure and regardless of electrical command. It also closes without electrical supply. The pack valve has 2 functions: pack shutoff and pressure and flow control. After passing the pack valve, the hot air flows through the primary heat exchanger where it is cooled. Immediately after, the air is compressed by the pack's centrifugal compressor where the air temperature rises again. After being compressed, the air passes through the secondary heat exchanger in order to have its temperature reduced. In the next step, the air is ducted to a condenser and a water extractor to be dried. The last stage is the expansion turbine section, where the air expands and becomes cold. Observe that after passing the expansion turbine, the air may become too cold. To maintain the selected temperature, it may be necessary to mix the cold air with hot air provided by a bypass duct. Now the air is ready for delivery to the cabin. The pack also has overheat protection. When the duct temperature downstream of the mixing chamber exceeds 88 degrees Celsius or 191 Fahrenheit, the limiter closes the temperature control valve progressively to reduce hot airflow. This is done pneumatically. When the duct temperature exceeds 92 degrees Celsius or 200 Fahrenheit and the pack valve doesn't close, you'll see an overheat caution. When the temperature downstream of the pack compressor exceeds 204 degrees Celsius or 393 Fahrenheit, the pack valve closes automatically. The temperature control system regulates and limits the temperature of the air that's discharged. The temperature control valve is responsible for mixing hot and cold air to meet the actual required temperature. In automatic mode, an electronic temperature controller controls the discharge temperature of each pack. This controller computes the temperature control valve position, taking the following into consideration: the duct temperature, the compartment temperature selector, the associated compartment temperature, and the aircraft skin temperature. The temperature panel is located on the overhead panel. It looks like this. Let's now go through all elements with a detailed explanation. In the center of the panel, you can see the compartment selector switch. It selects the zone, meaning flight compartment or cabin, that you want to read the temperature display for. Only one temperature indicator is installed. Thus, you have to use the compartment selector switch in order to have the information you want displayed on the temperature indicator. On top are the recirculation fan's push buttons. They select the operation of the recirculation fans. The modes are on, when the push button is depressed, and off, when the button is released. Each push button has an integrated fault light to indicate a failure of the respective recirculation fan. In mode on, the fan runs and recirculates a part of the cabin air to supplement the fresh air supply. Note that the fan rotation speed automatically varies from low speed to high speed depending on the temperature control valve position and the temperature measured at the cabin floor level. In mode off, the fan is stopped. All the air in the aircraft is now supplied by the packs without any recirculation. The off light illuminates white. In case of a recirculation fan low RPM or overheat, the fault light illuminates amber and the CCAS is activated. Just below this, you see the temperature selection push buttons. They select the temperature control mode operation. The modes are automatic, when push button is depressed, and manual, when push button is released. Each push button has an integrated overheat indication light. In automatic mode, the electronic temperature controller automatically controls the temperature control valve position. In manual mode, the compartment temperature selector rotary knob directly controls the position of the temperature control valve. For this mode, A pneumatic temperature limiter limits the maximum duct temperature. The manual light illuminates white. Whenever the temperature in the duct becomes higher than 92 degrees Celsius or 200 Fahrenheit, the overheat light illuminates amber and the CCAS is activated. Note that this function is not inhibited in manual mode. Underneath, you find the pack valve's push button. The modes are on, when push button is depressed, and off when push button is released. In mode on, the associated pack valve is opened if electrical supply and air pressure are available. In mode off, the associated pack valve is closed. The off light illuminates white. These push buttons have an integrated fault light. The fault light illuminates amber if the position of the pack valve disagrees with the selected position, or when an overheat has been detected downstream of the pack compressor. The CCAS will also be activated. In the middle top, we have the compartment temperature indicator. It indicates the temperature for the compartment selected with the compartment selector switch. The indication is in degrees Celsius. Close by, there is the duct temperature indicator. This one indicates the temperature of the conditioned air before leaving the duct for the selected compartment. It is also indicated in degrees Celsius. Underneath the compartment selector, you see the flow push button, which can change the flow mode of the pack valves. The modes are normal when the button is released and high when the push button is depressed. In mode normal, both pack valves are controlled to give a standard pressure. In mode high, both pack valves are controlled to give higher pressure, thus increasing the airflow in the duct. The push button integrated highlight illuminates blue. The last element is the ground crossfeed. It shows the position of the ground crossfeed valve. The amber ground crossfeed open light will illuminate if the ground crossfeed valve is open. In this case, the CCAS is not activated. The ATR 72 has a pressurized cabin. The pressurization system controls the cabin altitude and rate of change by either a fully automatic digital electronic controller or a manual pneumatic controller. In either case, the system ensures optimal outflow of conditioned air for the comfort of passengers and crew members. An electro-pneumatic outflow valve and a pneumatic outflow valve are installed at the end of the pressurized area. Both valves are fitted with safety devices in case the respective controller fails. The safety devices will limit the positive differential pressure to 6.35 psi and the negative differential pressure to minus 0.5 psi. Take a look at the table to learn more about the limitations related to the pressurization system. The pressurization system has two modes of operation: the automatic mode and the manual mode. In the automatic mode, the digital electronic controller sets the position of the outflow valves during all phases of flight, taking into account the following parameters: the landing elevation from the landing elevation selector, the takeoff elevation memorized by the digital controller, the cabin pressure, and the aircraft static pressure. The aircraft static pressure is generated by the Air Data Computer 1 and the actual captain's altimeter barometric setting, or in case of Computer 1 failure, by the Air Data Computer 2 with a 1013.2 hectopascal reference 29.92 inches mercury. Based on those parameters, the digital electronic controller computes the theoretical cabin altitude and sends a signal to the electro-pneumatic outflow valve torque motor to adjust the actual cabin altitude. In case of loss of electrical signal, the valve closes automatically. When operating in the automatic mode, the manual rate knob shall be selected to normal position to avoid disturbance of the automatic regulation. The automatic mode is fitted with the dump function. When depressing the dump push button, the digital electronic controller is deactivated, and a signal is sent to the electro-pneumatic outflow valve in order to keep it fully opened. This action also opens the pneumatic outflow valve. The dump push button is mechanically protected, and there's no other safety device protecting against its inadvertent use. It shall only be used when required by the Quick Reference Handbook, QRH. In the manual mode, the electro-pneumatic outflow valve is maintained closed, and only the pneumatic outflow valve controls the cabin outlet airflow. Any change in the cabin pressure shall be done via the manual rate knob. The manual mode is only used when the automatic mode fails. A ditching function is available for both automatic and manual modes. When the ditching push button is depressed, a signal is sent to maintain both outflow valves closed. It shall only be used when required by the Quick Reference Handbook, QRH. The digital electronic controller is electrically supplied by DC bus 1, and the DC emergency bus feeds the cabin pressure indicator and the pneumatic outflow valves. Some alerts are provided in order to inform the crew members about a system malfunction. If the cabin altitude is above 10,000 feet, the red master warning light flashes. Excess cabin altitude red warning is displayed on the CAP, and a continuous repetitive chime is generated. If the cabin differential pressure exceeds 6.35 psi, the master warning red light flashes together with the continuous repetitive chime, and the excessive cabin delta P red light on the CAP illuminates. In case the digital controller fails, the amber master caution light flashes. Air amber light is displayed on the CAP, and the fault amber light will illuminate on the mode push button. A single chime is generated by the CCAS. If the ditch push button is depressed, the amber master caution light flashes. Air amber light is displayed on the CAP, and the ditch push button on light illuminates white. A single chime is generated by the CCAS. The controls for the pressurization system automatic mode are located on the automatic pressurization panel. The landing elevation indicator displays the landing elevation in feet. The two last digits always display 0. The elevation set trigger switch allows the selection of the elevation of the planned destination airport in 100-foot increments. From minus 1,500 feet to 9,900 feet. The descent rate push button allows a faster cabin rate of descent. In the normal position, when the push button is released, the maximum cabin rate of descent is 400 feet per minute. In the fast position, when the push button is depressed, the maximum cabin rate of descent is 500 feet per minute. When the fast mode is used, a fast light illuminates blue in the push button. By pressing and holding the Test push button down, the system is electrically tested. The test is considered accomplished when the landing elevation indicator displays alternately 18,800 and minus 8,800, and the mode push button fault light illuminates amber. This test is inhibited in flight. The controls for the pressurization system manual mode are located on the manual pressurization control panel. The mode push button selects the pressurization system to operate in automatic mode when the push button is depressed, or manual mode when the push button is released. If the manual mode is selected, the digital controller is out of operation. The landing elevation digits are extinguished, and the manual controller regulates the cabin pressure. The integrated manual light illuminates white. The manual rate knob is used in the manual mode to select any cabin rate of change from minus 1,500 feet per minute to plus 2,500 feet per minute. The following steps must be followed in order to avoid pressure transients when changing from automatic mode to manual mode or vice versa. To switch from automatic mode to manual mode, you have to turn the manual rate knob to manual position. Select manual mode by using the cabin pressure mode select push button. Operate the manual rate knob as required to set cabin rate of change. To switch from manual mode to automatic mode, you have to disengage the manual mode by using the cabin pressure mode selection push button, and turn the manual rate knob smoothly to normal position. A cabin pressure indicator is installed to monitor the cabin altitude, the cabin rate of climb or descent, and the cabin differential pressure. The altitude indicator displays the cabin pressure altitude in thousands of feet based on 1013.2 hectopascal, 29.92 inches mercury. The rate indicator displays the cabin rate of change in feet per minute times 1,000. The differential pressure indicator displays the differential pressure between the cabin pressure and aircraft static pressure from -1 to +8 psi. A red flag on the right top of the panel appears to indicate a loss of power supply to the cabin pressure indicator. In the ATR 72, the air ventilation uses ambient airflow to ventilate and cool down the aircraft compartments and equipment. In this chapter, you'll learn how the ventilation of the ATR 72 works and how to control it. You'll also learn about the electrical supply and the alerts related to this system. First, let's take a look at the basics of the ventilation system. The air ventilation of the ATR 72 works in a very simple way. It has a general air inlet, packs, outflow valves, an air outlet, and a toilet ventilation line. The conditioned air is blown into the cabin by outlet ramps. They're located under the overhead bins. The air is then evacuated through guides along the cabin sidewalls at floor level. A part of the air is recirculated by the fans. Outflow valves evacuate the other part of the air to the outside of the aircraft. Note that the toilet is ventilated by differential pressure through a vent line. The position of the outflow valves automatically or manually controls the pressure and the pressure variations in the pressurized compartments. The cabin ambient air ventilates the electric and electronic equipment and the forward cargo compartment, and then is extracted by a fan. In case of fan failure, the ventilation is accomplished by cabin differential pressure. In the ATR 72, the flight deck, the electric and electronic equipment, and the forward cargo compartment are all ventilated by ambient airflow that's distributed by the packs. The air is then either recirculated in the pressurized compartment or ducted overboard at the avionics equipment outlet. The system uses two valves in order to ensure correct flow of the air. The overboard valve, which in fact controls the underfloor valve. When the overboard valve is fully closed, the underfloor valve is opened. When the overboard valve is partially or fully opened, the underfloor valve will close. The overboard valve can operate in two modes, the automatic or the manual mode. In the automatic mode, which is the normal mode of operation, the position of the overboard valve is automatically set. Note that in the FCOM, the automatic mode is mentioned as normal mode. The manual mode is to be used in case of failure of the automatic mode or on ground to accelerate cabin heating by selecting the full closed position. To change the mode of operation, you simply have to change the position of the overboard valve control switch located on the avionics ventilation panel. Be aware, do not open the overboard valve manually if the differential pressure is higher than 1 psi. An extract fan installed in the ventilation system generates suction and forces air ventilation. The main purpose of the extract fan is to extract hot air from the avionics compartment. The fan operates automatically at different speeds depending on the flight deck temperature. It works at minimum speed below 20 degrees Celsius and at maximum speed above 52 degrees Celsius. The speed varies linearly between these values. The extract fan is controlled by the exhaust mode push button. Its normal position is depressed, and two different situations occur. When the aircraft is on ground and engine number 1 is not running, the extract fan runs continuously. The overboard valve is fully open and the underfloor valve fully closed. In flight or on ground with engine number 1 running, the extract fan runs continuously. The overboard valve is fully closed and the underfloor valve fully open. In flight only, if the extract fan fails, you may use the exhaust mode push button to set the overboard valve in a partially open position in order to provide cooling airflow by cabin differential pressure. This is only possible when the overboard valve is operating in the automatic mode. At this point, let's assume you're in flight and the extraction fan fails. Now, if the overboard valve mode is selected to automatic mode, you can then use the exhaust mode push button to keep the overboard valve partially opened. As described earlier, the flight deck is ventilated by air blown from the left pack. In case of smoke in the forward cargo compartment, you can close the flight deck air extraction duct with a lever located on the right side maintenance panel. This results in an increase of static pressure in the flight deck due to the permanent delivery of fresh air from the pack, which prevents smoke from entering the working environment. The extract airflow lever shall only be used when required by the Quick Reference Handbook, QRH. Now, let's look briefly at the electrical supply of the equipment related to the ventilation system. The overboard valve and the underfloor valve are supplied by the DC emergency bus. The extract fan control relay is supplied by the DC essential bus. The extract fan contactors are supplied by DC bus 1 and DC bus 2. For a complete list of the electrical supply, refer to the FCOM chapter Air. In the ATR 72, some alerts are provided in order to inform crew members of any failures related to the ventilation system. In case of a fan failure or overheat, the visual and aural alerts are: the master caution light flashes amber. The air amber light is displayed on the CAP. The exhaust mode fault amber light is displayed on the exhaust mode push button. A single chime is generated by the CCAS. If the overboard valve position is not in accord with the aircraft condition, the visual and aural alerts are: the master caution light flashes amber. The air amber light is displayed on the CAP. The fault amber light is displayed on the avionics ventilation panel, and a single chime is generated by the CCAS. When the aircraft is on ground with the overboard valve control operating in the automatic mode, the extract fan runs continuously. And as long as the engine 1 is not running, the overboard valve stays open. When all aircraft doors are closed, the extract fan suction will create a noticeable change in the cabin pressure.